It's able to record. Let me share my screen. I'm going to start the lecture. Let's see in chapter 1, session 2. We started last time. We talked about the state process cycle, zero law of thermodynamics, conversion of the units, and also we started definition for pressure. Pressure is normal compressive force per unit of area in a SI system. The unit is Pascal. Excuse me. We also talk about bar and atmosphere, PSI and PSF, which are pound per square inch and pound per square feet. And we got to a definition for absolute and gauge pressure. We talk about absolute and gauge pressure, and now we are at variation of pressure with depth. So last time I asked you a question. I asked you, what do we mean by pressure at a given point in the fluid? What does that mean? And the answer was, you consider a differential cubic around that point, such that that point is in the center of differential cubic, and that cubic has 6 surfaces. There is pressure on top, on bottom, right, left, front, and back surfaces. And then as the dimension of this fluid element approaches to 0, it becomes like a point, the very same point A. So pressure on the top surface and bottom surface, right, left, front, and back, they become pressure at point A on different surfaces you pass through A. In other words, that is the pressure at A when you are looking at A from different direction. Because when you talk about pressure, 2 things are involved: force and surface. So on which surface? Does it matter from which direction you are looking at point A? This direction or this direction or this direction? We are talking about pressure at point A, right? And the answer was, if there is no shear stress, if there is no shear, then pressure at any given point, like point A, is independent of direction you are looking at point A. Pressure is independent of direction. And when shear is 0, shear is 0 when there's no motion, like we are talking about water in a pool or water in the tank. No motion, no friction, even if fluid is viscous. And another case that shear stress is 0 is when viscosity in the fluid is viscosity of the fluid is negligible. Now that we know pressure in a stationary fluid, like when we talk about water in a pool or in a tank, pressure in a stationary fluid is independent of direction. It doesn't matter from which direction you are looking at point A. It doesn't matter, what's plane, what surface passes through A, and you consider pressure at point A on that surface, because pressure is force, normal force per unit of area. So it has to be normal to that plane at that given point. But it doesn't matter from which direction. All we need is just location of the point. Now, the second question comes, how we can calculate pressure at any random point, any arbitrary point in a stationary fluid. Say stationary fluid because when the shear stress is 0, we want the shear stress with 0. And even if the fluid is viscous, no motion, no friction. If there is no motion, there will be no friction between the fluid, between the layers of the fluid and between the fluid. We can prove that, I'm going to skip the proof. We can consider a differential element. And we can prove this formula that you are looking at. If you are at Z1, look at the axis, the way which was axis. Here is x-axis, here is z-axis, which is a vertical direction, and y-axis is perpendicular to the board, right? So when you are at this level in the fluid, for example, on this surface of the cubic, which is located at Z2, that is, surface 2, which is located at elevation 2, which is located at Z2. You measure it from origin, right? So this distance is Z2. I'll show it with this red arrow. And when you are at this level, level 1, on top surface of this cubic, it's located at Z1, right? Because you measure it from O, that is Z1. And difference in elevation is Z1 minus Z2. If you measure it from the free surface, for example, if this is water in a tank, and here is the free surface which is exposed to the atmosphere, you put this triangle to show the free surface. And surface 1, or top surface of this cubic, is at vertical distance h1. The distance between this surface, the vertical distance up to the free surface is h1. And the vertical distance between this surface up to the free surface is h2. Then we can prove this formula that P2, pressure on this surface, which is located at level 2, is P1, whatever pressure on top surfaces, plus gamma H. And H is H2 minus H1, difference. This vertical distance between these two level is H2 minus H1. Or, if you choose any random point, which is a vertical distance H, like this point, any random point like this point, which is that vertical distance from the free surface, pressure here at this given point, with some random point, is pressure on top of the water on the free surface, which is pressure of atmosphere in this case, because it's exposed to the atmosphere. So it's pressure of atmosphere plus the weight of this column of fluid, which is gamma H. By the way, gamma, in case you wonder what gamma is rho G. Rho is density of the fluid, which depends on the fluid, and G is gravitational acceleration. So gamma is rho G. Rho G is gamma. G is G, gravitational acceleration. In SI systems, 9.8 or 9.81, or to be exact, 9.807. And G, and in the other system, British system and English system, that is 32.2 feet per second square. In SI system, 9.8 meter per second square. Gravitational acceleration. And rho is density of the fluid. Rho G is gamma. And that is called a specific weight. Gamma is called a specific weight. So it's gamma, it's called a specific weight, and it's equal to rho G. The physical meaning of gamma, which is a specific weight, that is weight per unit of volume. Whenever you hear the word specific, like a specific weight, specific volume, it is, a specific weight is weight, per unit of volume. And because density is mass per unit of volume, and when you multiply by G, that becomes weight per unit of volume. So that is weight per unit of volume, rho G, specific weight. So gamma is called, one more time, a specific weight, and that mathematically it's equal to rho G, and the physical meaning is weight per unit of volume. And that makes perfect sense because rho is density, which is mass per unit of volume. Think about that. When you multiply by G, that becomes weight per unit of volume, which we call a specific volume because it's weight per unit of volume. That makes it specific. Right. So in order to calculate pressure anywhere in the fluid, all you need is pressure on top of the fluid on free surface, which is usually, if it's exposed to the atmosphere, it's pressure of atmosphere. We name pressure of atmosphere P naught or PATM, ATM for atmosphere. P naught because we usually use it as a reference. I'm going to explain in a second. And set it equal to 0. So P naught is pressure of atmosphere, PATM or P naught, plus gamma H. Gamma is a specific weight of the fluid, which depends on fluid. It's different when you go from one fluid to another. What is H? H is vertical distance between that point up to the free surface. You don't go this way. It's vertical distance. So H is vertical distance. So that is pressure at any random point at this point in the fluid. You need vertical distance between that point and up to the free surface. You need gamma, which is a specific weight. So you need density of the fluid and also pressure on top of a fluid, which in this case, it's exposed to the atmosphere. So it's going to be pressure of atmosphere. And if you consider these two levels, level 1 and level 2, pressure at level 2, pressure on any surface which is located at level 2 is pressure at level 1 plus gamma H. Gamma H is vertical distance between these two, which is basically H2 minus H1. This distance is H. And gamma is a specific. So it's easy to calculate. As you go deeper and deeper in the fluid, pressure becomes larger and larger. See, P2 is larger than P1. P2 is P1 plus something because the weight of the fluid increases. Pressure in the stationary fluid comes from the weight of the column of the fluid from here up to the end. For example, the pressure of the atmosphere at the sea level comes from the weight of the atmosphere from the sea level up to the end of the atmosphere, which is gamma H, comes from weight. So all the points located on the same level, they experience the same pressure. Look at this formula. Pressure is P naught plus gamma H. So if you are in the same fluid, it means gamma is the same. If you move in the same fluid, gamma is the same. And P naught is the same, the pressure on top. So all the points located on the same vertical distance to the free surface, they experience the same pressure because for them, H is the same. Consider this lake. We assume that's stationary. And this is the free surface, and here is the bottom, right? Compare the pressure at point A, B, C. What is the pressure? We are talking about pressure exerted on the surface through water. Pressure, direction for pressure, do not forget, is always normal and compressive to the surface at that point. It is normal compressive to the surface at that point. So consider this point, normal compressive to the surface at that point. Normal compressive, normal compressive. So at A, here is the direction. At B, here is the direction. At C, here is the direction, right? How do you calculate value, magnitude? It is gamma H. P naught, which is pressure on top, which is pressure of atmosphere, that is the free surface, plus gamma H. What is gamma? It's rho G. That is called a specific weight. It's weight per unit of volume of fluid, weight of 1 unit of volume of fluid, rho G. So we can calculate rho G if we have density. And what is H? Vertical distance. Do not go this way. Vertical distance between that point up to the free surface. So it's always vertical distance. See, vertical distance. So, and because for A, B, and C, they are all located in the same fluid, H is the same for all of them. And pressure on top, P naught is the same for all of them. And because H is the same, they are all located in the same level, in the same fluid, they experience the same pressure because H is the same. By the way, so for PA, PB, PC, they're all gamma H. You may ask me, you should add P naught. Yes. If you want to calculate pressure at A, B, C in terms of absolute the absolute pressure, you add P naught. But so that shows the pressure at this point in terms of absolute. But if you want to express it in terms of gauge and you want to go gauge, then you say, you know what? I know this is not zero. That's the pressure of atmosphere on top of it, but I use it as a reference. When you use the pressure of atmosphere as a reference, you set it equal to zero and you measure pressure of everything relative to pressure of atmosphere. It is the excess of pressure over the pressure of atmosphere. Set it equal to zero. If you set this equal to zero, then P becomes gamma H. And now P is expressed in terms of gauge. So that is the gauge fluid at this. So gauge fluid at A, B, and C. A, B, C is gamma because you set the pressure of atmosphere at zero. Is there any question? Please give me some confirmation. No question, there's question. So,
No question.
guys?
Professor, so if the liquid was different from A to B and there was another liquid from that C little location, it would have been different, right?
Yes, if you go from one liquid to another, of course. If you have two containers and in one there is water and the other one there is oil, 2 points, we are at the same location, they experience different because although H is the same, but gamma is not the same. But here, A, B, C, they are all in the same fluid and the same level. So under a note, I wrote that points at the same level and the same fluid, they experience the same pressure. And that's very simple, but very important. We are going to use this simple fact, this simple principle in some devices like, hydraulic lifts, elevators, car jacks, and this type of, devices. We use them in these machines. So consider, I'm going to explain on this example. So there is a fluid in there and it's piston cylinder on both sides. The area of piston here at left side, which we name A1, is an A2, right? And we know that these two surfaces, I'm talking about the bottom surface of the piston. Think about that, the bottom surface of the piston. They're at the same level. So they experience the same pressure from the fluid. So fluid exerts the same pressure on the bottom surface of piston A and on the bottom surface of piston 2. Because if here the pressure was larger than here, it goes up. If the pressure here is larger, it goes up. So pressure is the same. Points located on the same level, the same fluid, they experience the same pressure. See all the points on the bottom level of piston 1 and all the points located on bottom surface of piston 2, they are at the same level, the same fluid, they experience the same pressure. So based on that, we can say points, same level, same fluid, experience the same pressure. So P1 is equal to P2. By the way, it's uniformly distributed for all the points. It's the same. Pressure is the same. Uniformly distributed. So P1 is equal to P2. What is P? We know pressure is force per unit of area. So if it's at equilibrium, there is a force on top, which should be equal to, that is external force from the bottom, from the liquid on the piston. Because if this force was larger than force exerted on the piston, from the bottom, it goes up and vice versa. So when it's at equilibrium, when there is no movement, it means F1 it is equal to force coming from this pressure. And because pressure is force per unit of area, force is pressure multiplied by area. So see, we say P1 is equal to P2. What is P1? It's F1 divided by area of piston 1, because pressure is force per unit of area. What is P2? We are going to substitute for P2. Pressure is force per unit of area. So it's going to be F2 divided by A2. Based on that, F2 is going to be F1 multiplied by ratio between A2 and A1, A2 over A1. So if you make this machine such that A2 is way larger than A1, with a small force like F1 that you exert, you can create very large force. That's what is being used in car jets, in hydraulic lifts, and these type of machines. So you can create a large force here with a small force F1 that you exert here, just by ratio between these two, if A2 is way larger than A1. Is there any question before I proceed? So that very simple concept that points on the same level, the same fluid experience, the same pressure, we use that in making these machines. Now, I want to talk about manometer. We use manometer to measure the pressure of the fluid. And there is U-tube manometer. Here is U because it has the shape of U. So that's U-tube manometer. We use U-tube manometer for two things. Measure the pressure of the fluid at some point and measure the pressure difference. For example, in fluid mechanics, you will see the application. Sometimes you want to measure the pressure difference between two points of a pipe. We are talking about fluid mechanics, fluid dynamics, when we talk about fluid in pipe, because fluid has motion, it's dynamic, fluid dynamics, but we don't care that fluid has motion in the pipe. Fluid is stationary within the U-tube, and we can use what we just learned in order to calculate pressure when the fluid is stationary. This formula you can only use if the fluid is stationary, because no motion or friction. In order to measure the pressure, remember we said if there is no motion, there is no friction. If there is no friction, pressure at any given point is independent of direction. So it doesn't matter which direction, just give me point A and I give you the pressure. And then the next question was, okay, how I can calculate, and then we come up with this formula. This formula only used when the fluid is stationary. So here, and fluid between the U-tube is stationary. So we use U-tube manometer for two things: measure the pressure in the fluid and measure the pressure difference in the fluid between 2 points. Now, when you want to measure the pressure of the fluid, you connect this U-tube manometer into a container. By the way, this U-tube manometer has liquid of its own, which is called gauge fluid. And usually it is mercury, because among all of the liquids, mercury has the highest density. So we use mercury, Hg, mercury. That's called gauge fluid. And one end of U-tube is open to the atmosphere. The other end you connect to the container that you want to measure the pressure of. So here it's some sort of fluid. In this case, it's gas, because if it's not gas, it's going to be a bit different. I'm going to explain how. See, the pressure of this gas, because it's gas, it has low density. So it doesn't matter if you talking about pressure here or pressure here or pressure here. You know why? Because for gas with low density, maybe if you're talking about 100 feet, that makes a pressure difference. You go from here to here, you go up and down, and it's 100 feet or 10 feet, but not for such a small distance. Pressure here doesn't differ much from pressure here. So, but if it was liquid, it does matter. So you say, okay, pressure, whatever pressure here is pressure P1 plus gamma H, and then, so it would be different. But for gas, doesn't matter. So you say, okay, pressure inside this container, it can be pressure, let's say here, it's the same as you go horizontal and pressure doesn't change, and you go down and pressure doesn't change. And you are here. then you go horizontal from point 1 to point 2. And because you go horizontal, pressure doesn't change because points which are on the same liquid, in the same level in the fluid, they experience the same pressure. So you are looking for, you say, okay, P1 is equal to P2, right? And how do you measure P2? Pressure here on top of the surface is the pressure of atmosphere, which is on top, plus the weight of this column of fluid, which is gamma H. So it's P of the atmosphere, which is pressure on top of the surface, plus gamma H, and that is P2. And P2 is the same as P1 because they are in the same fluid, the same level. You may ask me, here it is on the border. Doesn't matter. You can consider it as a part of this fluid or this fluid. So anyhow, these 2 points, 1 and 2, they are on the same level, the same fluid. So P1 is equal to P2. And P2 is P of the atmosphere, which is pressure on top, plus weight of this column of the fluid, which is gamma H. So P of atmosphere plus gamma H is P1. That's where you can measure pressure here on top of this surface, which is nothing but pressure of this gas. So we are able to measure pressure of the gas. And that is in terms of absolute. That's P1 expressed as absolute pressure. If you set pressure of atmosphere 0 because you are using it as a reference, then you have P1 being equal to gamma H. Now you express P1 in terms of gauge. So the gauge pressure of P1 in terms of gauge, which is gauge pressure of this fluid, this gas, is equal to gamma H. So you look at the U-tube, and in one leg, the liquid, which is mercury or gauge fluid, right? And you multiply that distance H by gamma, and that gives you pressure. So that's how we measure the pressure using U-tube. By the way, gamma is a specific weight of gauge fluid, which is usually mercury. And gamma, which is called a specific weight, you know how to calculate it. That's rho G, density of the gauge fluid times gravitational acceleration, G. And here we set the pressure of atmosphere 0. That's why P1 is expressed and measured in terms of gauge. And P1 is nothing but pressure of this gas. Right? Is there any question?
No, Professor, thank you.
What's that?
I don't have any questions, Professor, thanks.
Okay.
Professor, sorry, but I actually have a question. Is this to measure like the pressure that's outside, or are we measuring the pressure that like the fluid
You're measuring the
inside?
pressure of the fluid inside this container, which is gas in this case. Because if it was not gas, you have to consider the pressure of the weight of this column of the fluid too. But because it's gas and density of gas is small, you say, okay, weight is negligible. So pressure anywhere is the same. So you just measure the pressure on top of this surface, which is basically the pressure of this gas. Yes, the container, not outside, just this container. See, P1 is the parameter of interest, right?
Mm-hmm. Cool. Thank you.
Okay, yeah, of course. Now we want to see how we can use the U-tube to measure the pressure difference between, 2 points, pressure difference. In previous case, we use it to measure just the pressure. Here is the pressure difference. So you connect this U-tube between 2 points that you are interested in, because when you take fluid mechanics, you see when you want to use Bernoulli or energy equation, you need pressure difference between 2 points of the pipe, and sometimes you want to measure volume flow rate in the pipe, and you need to measure the pressure difference between 2 points of the pipe first. So you make use of this U-tube monometer and you connect it to 2 points that you want to measure the pressure difference. Let's say it's 0.1 and 2. Inside the pipe, we are talking fluid dynamics because a fluid has motion. But within this U2, fluid is stationary. So we are talking about fluid statics. So we start from 0.1, try to reach to the other point in order to measure pressure difference within the U-tube, not through the pipe, within the U-tube. So we start from here. Pressure here is P1. You are interested in P1 minus P2, which is pressure difference between these 2 points. So P1, then you go down by H1. And whenever you go down, pressure increases because as you go, deeper and deeper in the fluid, pressure increases. As you go up, pressure decreases because of the weight of the fluid. So it's P1, and then you go down, it's plus because pressure increases. By how much? By this distance, which is H1, multiplied by gamma 1. Gamma 1 is a specific weight of this fluid, which is fluid inside the pipe of fluid, F for fluid. And then when you reach here, you just go horizontal. Nothing changes because if you compare this point and this point, let's say point 3 and 4, they are both in the same level, the same fluid. So nothing changes, only if you go up and down. Then when you reach to the other leg here, 0.4, you go up in order to reach to 0.2. You want to start from 1, try to reach to 2 through the U2. You go up, and as you go up, pressure decreases. So there is minus. By how much? By H, this distance multiplied by gamma, which is a specific weight of this fluid, which is gauge fluid, G for gauge. And then we reach this point. We still need to go up by how much? By H2. And if you go up, pressure decreases by how much? H2 minus, so it's minus H2. And that is gamma of the fluid, which is fluid in the pipe. And then you reach 2.2. So that is equal to pressure at 0.2. We are interested in P1 minus P2. Why you subtract P2 minus P1? Because here is the direction for flowing fluid, and fluid always move from higher pressure to lower pressure, higher to lower. So P1 should be greater than P2. So it's P1 minus P2, and take the rest of the terms to the other side. But look at the geometry. Isn't H plus H2 equal to H1? Yes, it is. So for these two, if you factor out gamma of the fluid, these two terms, this term and this term, gamma of the fluid, then you have H1 minus H2. See, H1 minus H2, that's going to be H. So it's gamma of the fluid times H, right? With the minus sign, gamma of the fluid times H with the minus sign, and you take it to the other side. And then here is the other term, H, gamma of the gauge fluid with the plus sign, and you take it to the other side. You can factor out H, so it's going to be H on the other side, gamma of the G, gamma of the gauge fluid, minus gamma of the F. So here is the thing, see, it's G, right? And it's gamma of the G minus gamma of the F. That's how you calculate P1 minus P2. So it's P1 minus P2, because we know P1 is higher than P2, because here is the direction of flowing fluid. So pressure 1 should be larger than 2. And that's going to be, you look at the U2, and in one leg, fluid rises by how much? By H. When you compare these two legs, fluid rises by H. So it's H, that's rising gauge fluid. And you multiply by not gamma of the gauge fluid, gamma of the gauge fluid minus gamma of the fluid in the pipe. And it's always like that. Gamma of the gauge fluid minus gamma of the fluid in pipe. So it's P1 minus P2 being equal to, look at the U2. In one leg, the gauge fluid rises by H. And you multiply by gamma of the gauge fluid, which is mercury, minus gamma of the fluid in the pipe. So that way you can calculate pressure difference. Is there any question, guys? So keep that in mind. Whenever you go down, pressure increases because of the weight of the fluid. Whenever you go, so pressure here is larger than here. If you go down, when you go up, pressure decreases because pressure here on top is less than pressure here. As you go deeper and deeper, pressure increases. One more thing you need to know, pressure, for the fluid dynamic, the pipe fluid has motion. So it involves fluid dynamics, but within the U-tube, it involves fluid static because it has no motion. And that's why you can use this formula, gamma H is equal to P, because fluid is stationary within the U-tube. Any question? All right. Let's go and talk about measuring pressure with multi-fluid monometer. By the way, whenever the time is up, let me know, because sometimes I lose the track of time and so let me know when it's up. Measuring pressure with a multi-fluid monometer. We want to determine the pressure of air here. There is air here. We want to measure the pressure of air. I'm going to explain that I ask you to do that. I ask if there is any volunteer. So there is the container, there is the air here. We are interested in pressure of air, which is P1, pressure on top of the fluid. And there is water. Up to here, there is water. And then from here, 0.2 to 0.3 in this U2, there is mercury, which is the gauge fluid. And then from 0.3 up to 0.5, that is oil. So from here, we just follow up to here, 3 to 5, that is oil. And then here it exposed to, I think, H3. Let me see if H3, because I have dash here. Oh, okay. You know what? This part is oil. This part, only this part from 5 to 6 is oil. All the way from 2 to 5, that is mercury. All right. So one more time, there's a container. We are interested in pressure of air here, which is on top of this fluid. And here's water up to 0.2. And here is, U2, and all the way from 2 to 3 to 4 to 5. That's, I used oil here. Let me see. Oh, no. Up to 4. I wish I used a color marker. Even I am confused. So from 2 to 3 to 4, it is mercury. From 4 to 5 and 6, it's oil. And at 0.6, it's exposed to the atmosphere. Now I give you a few minutes to set up the equation to calculate pressure on top of this container, which is pressure of air. So water up to 2, 2 to 3 to 4, it's mercury. And then see the dash line changed from 4 up to here, 6, it is oil, and then it's exposed to atmosphere. I'll give you a few minutes.
Professor, I have a question.
Yes.
So at the end that we reach the gamma of oil times H3, why don't we write plus P of atmosphere? Why do we just say that's equal to atmosphere?
It is equal to pressure of atmosphere. Yes. At the end,
because at the end, while we're moving H3 and then up, so it should be negative H3, which you have it over there. But then why don't we say another negative because we're going up to reach the air, correct? So why don't we say negative
See,
P of
when
atmosphere?
you add all of those, then you reach here, pressure here on top is equal to pressure of atmosphere, right? So
Oh,
you
okay.
start from one end, try to reach to the other end through this YouTube. When you reach to this point, right? Then you know at this point it is equal to pressure of atmosphere, right?
Yeah, that makes sense. Thanks.
Mhm. Of course. Is there anyone who wants to explain?
I can explain.
Yes, please.
Okay, so as always, like as you shared above, so we're going to start from the point P1 and we're going to write pressure at point P1 equals, not equals. So while we're going down to reach that point, since we're going down, it's going to be another positive gamma H1 since we're going down one. So but that point, it's equal to 0.2 and it's equal to 0.3. So we go horizontally and we reach 0.3. So from 0.3, we go down again. And since we're going down, it's going to be another positive and then H2 and then gamma of that liquid, which we have over there. And then we reach 0.4 and then we move another horizontally since we know that it's going to be the same pressure at the other end. So we reach at 0.5 and from 0.5, we are going up. So it's going to be a negative H3 gamma of that liquid over there. And then as you explained, it's going to be equals to the pressure atmosphere. And then that's going to be 0. So from the following, we can write the equation that you have over there, Professor.
You explained perfectly. Thank you. So as your friend just explained, we start from, one and try to reach to the other end through this YouTube. So pressure here is P1 and then you go down by H1, that is through water. So pressure increases as you go down by H1 gamma of the water, and then you go horizontal from 1 to 2, nothing changes, the same fluid, the same level, and then you go from 2 to 3, nothing changes, the same fluid, the same level, and then you go down by H2, pressure increases, so it's plus by how much, but H2, and that is gamma of the mercury, then you reach to 0.4, and then you go from 4 to 5, and then nothing changes, the same level, the same fluid, and then you go up, pressure decreases by gamma of the OH3, and then you reach 0.6, which is basically here it's exposed to the atmosphere, so it's equal to pressure atmosphere in the gauge sense. In the gauge scale, that is 0. So pressure, we just take all of those terms to the other side. Thank you. And your name? I forgot your name.
Professor, I'm Harriet Yousefi.
Okay, thank you.
Thank
You
you.
explained it perfectly. Thanks. So let me see. We go to the next one. We want to, talk about a barometer. Barometer we use in order to measure the pressure of atmosphere. And if you fill this tube with if you fill this tube with, mercury. We use mercury because it has, high density among all the liquids. It's basically, liquid metal, right? And you turn it upside down, you invert it into this container. You know that pressure at B, it's exposed to the atmosphere. It's the pressure of atmosphere, because on top of this free surface, the pressure of atmosphere. So pressure at B is equal to pressure atmosphere, and you are looking for pressure atmosphere. So all you have to do is just measure pressure at B. And pressure at B is the same as pressure at A, because they are on the same level, the same liquid. And pressure at A is the weight of this column of fluid, which is gamma of the mercury, or gamma of whatever the fluid is, multiplied by H, plus, because it was filled originally, but there is a small, very small space here, which is like a vacuum. So the molecules are free to fill this space, but the pressure is really, really small. It's negligible compared to the weight of this fluid. So basically, the weight of this fluid, which is gamma H, is pressure at B, right? And that's how we measure the pressure of atmosphere. But here is the thing: if you use water instead of mercury, this height would be as high as 10.3 meter. That's why we use, mercury, which has high density. By the way, if we go higher and higher, for example, if you climb the mountain, you do know that the pressure of atmosphere decreases because it comes from the weight of the atmosphere, right? So the weight of the atmosphere from wherever you are up to the end. And, when you go higher and higher in elevation, the pressure of atmosphere decreases, and so is the boiling temperature. For example, boiling temperature of water. We talk about this stuff in detail in fluid mechanics as we get to vapor pressure. Is there a question? Yes or no?
No, Professor.
All righty. We are done with this one. Let me just, okay. Let
Professor,
us go. Yes,
will you upload that notes on the campus or not?
I'm going to send it via email to you guys. And, if I can, yes, I will upload it in the campus too. Let me
Yeah,
see.
please.
We are in session 2, chapter 1. You can see my okay, let me stop sharing for a second to find it. And then, okay. Chapter 1, session, is there session 2? I believe not. So we can move to chapter 2. Yeah, chapter 2, session 1. All right. One thing that I need to explain, and I haven't, is I want to explain specific hits, but I don't have them in a slide. Later on I will, but I think I have to include this before I send it out. So chapter 2, session 1. This is chapter, I don't get it. Just give me a sec. Oh. Chapter 2, session 1. All right. Let me share my screen first. All righty. And go to, oh, everything is chapter 2, session 3, chapter 2, session. I have lots of slides sometimes. Okay. Chapter 2 we want to talk about, first law of thermodynamics. Okay, so see, first law of thermodynamics is nothing but energy balance equation, and that is based on conservation of energy. I wonder why didn't I talk about conservation of energy before and first law? Oh no, for the other class I did, because I never had, okay. So first law is nothing but energy balance equation, and that's based on conservation of energy. What does conservation of energy tells us? It's very simple. Energy cannot be created or it cannot be destroyed, right? So energy cannot be created or it cannot be destroyed. Based on that, we form energy balance equation. We apply it to different devices and we try to substitute for the terms in the energy balance equation, and then we see the application. There are lots of application that's engineering. We are going to apply it to different engineering device, and I include lots of examples in the lecture for you guys. So if this is a system, if this is a system, just look at it like a blackboard. It can be anything. It can be, the heat exchanger. It can be, duct. It can be a section of pipe. It can be turbine. It can be pump. It can be anything. But we don't care at this point. If there is some energy transfer into the system, and there are some energy transfer out of the system, E in minus E out, if these two don't balance, what happens to the difference? The difference goes toward the change of energy of the system, right? So how do you read this? You say capital E for total energy transfer into the system minus total energy transfer out of the system. The difference is a change of energy of the system. For example, if 10 units of energy transfer into the system and 7 units of energy transfer out of the system, 10 minus 7, which is 3, that is a change of energy of the system. And that's nothing but, first law. So you're looking at the first law. But what we do, we are going to explain each parameter here, and then we are going to plug in into this formula for different devices and make the first law for different devices. But you're looking at the first law right now, and that is based on conservation of energy. Keep that in mind. By the way, this is audio recorded. So, during a process, the total energy transfer into the system minus the total energy transfer out of the system, that is change of energy of the system during a process. Now, we want to work on different parts of this formula, then put everything back together. But right now, be focused on this term. What is the change of energy of the system during this process? What do we mean? The system undergoes a process. For example, it goes from a state 1 to a state 2, and we say during this process, all the energy going to this system minus all energy taking out of the system, that is change of energy of the system. Okay, look at this figure. Take a snapshot of this figure in your mind. It's very useful. Change of energy of the system, isn't it? Energy of the system at the final state minus energy of the system at the initial state. If I tell you that energy is a point function, so energy is a point function. So when you know the state, the value of energy, for example, like temperature, like pressure, right? So you're at a state 1, temperature is T1, pressure is P1, and energy is E1. Then you are at a state 2, pressure is P2, temperature is T2, and energy is E2. So what is change of energy of the system? It goes from a state 1 to a state 2. during the process. So it's E2 minus E1, right? That's change. So change of the energy of the system is energy of the system at the final state minus energy of the system at the initial state, right? And that's change of energy of the system. And so that's how you calculate change of energy of the system. But in another word to explain that, so we know that's how you calculate energy of the system. That energy of the system that includes changing kinetic energy, changing potential energy, and changing internal energy. So change in energy of the system that includes, when we're talking about change of energy of the system, we should think of, okay, changing kinetic energy of the system, changing potential energy of the system, and changing internal energy of the system. So again, remember, we just focus on right side of this equation. We want to see, what do we mean by change of energy of the system? We mean changing kinetic energy of the system, delta Ke, change in potential energy of the system, delta PE, and change in internal energy of the system, delta U, right? Or we can measure it this way: energy of the system at the state 2 minus energy of system at the state 1. That is change during this process that takes the system from a state 1 to a state 2. Under this note, I mentioned that energy is a property, it's a point function, is a property value. And when you go from one state to another state, the energy changes. At a state 1, the value of energy, its point value, like temperature and pressure, is E1, at a state 2 is E2, right? And if the state of the system doesn't change, it means the energy of the system doesn't change. If you are at the same state, the temperature is the same, the pressure is the same, and so is the energy, right? So if the state of the system doesn't changes, then energy of the system doesn't change. Remember previously, in previous session, we talked about cycle. A cycle, in the cycle, the initial and final state, they are the same. So what do you think? What is the change of energy of the system if it undergoes the cycle? I give you 1 minute and then volunteer answer. Any of you guys can explain it and tells us right now. What is the change of energy of the system if the system undergoes a cycle? What can you say about change of energy of the system? The system undergoes a cycle. Anyone? Guys, I'm waiting. And previously, I explained that in the previous session. Anyone? Give me something.
Professor, wasn't that the output minus input? As in, yeah.
See,
As in
if
the final minus initial?
isn't it 0? Because if it's cycle, the final state and initial state is the same. It's cycle, right? So it starts from a state and it's a cycle. So it goes back to very same state, right? So there will be no change. There will be no change in the energy of the system, right? Do you agree?
Yes.
So if, system undergo the cycle, there will be no change in the energy of the system. So delta E of the system would be 0 because initial state and final states are the same. And by the way, change of energy of the system, you can break it down into 3 parts: change of internal energy, change in kinetic energy, and change in potential energy. Change in internal energy, which is mu2 minus u1, change in kinetic energy, which is half of mv2 square minus v1 square, and change in potential energy, which is mg v2 minus v1, right? So part of delta E of the system is changing kinetic energy and changing potential energy and changing internal energy. So I just explained that the right side of energy balance equation because there is a system. The system can be a pipe, it can be duct, it can be anything. Just look at it as a black box, and there is some energy transfer into the system. There is some energy transfer out of the system. The difference between these two, if they don't balance, is change of energy of the system according to conservation of energy, because energy cannot be created or destroyed. So we are talking about this equation, energy balance equation, and this system. And right now we just focus on this part, not this part. And change of energy of the system, during the process of energy of the system at final state, it goes from a state 1 to a state 2. So what is the change in energy of the system? It's energy at the state 2 minus energy at the state 1, because it's point function. But it also can be calculated using this way. You say, okay, I can break it down into changing internal energy, changing kinetic energy, and changing potential energy. So it's delta KE, delta PE, and delta U, like I explained here, right? So here on this slide, I show it mathematically. Delta U with the change of energy. I use capital U because it's for the whole system with a mass M. That is U2 minus U1. That is delta lowercase u, which is changing internal energy per unit of mass. Then you multiply by mass, and that becomes changing internal energy for the whole mass, for the whole system. And changing kinetic energy and changing potential energy are used, uppercase for both. So changing kinetic energy is half of mv2 squared minus v1 squared. That's the velocity at the state 2 velocity. For example, velocity at the outlet, velocity at the inlet of the pipe. And changing potential energy is mgz2 minus z1. That's elevation. So again, I summarize it here in this slide. Changing energy of the system is energy at the state 2 minus energy at the state 1. It's changing internal energy, kinetic energy, and potential energy. And here you substitute for delta U, delta KE, and delta PE. Here is changing kinetic energy, here is changing potential energy, and here is changing internal. Is there any question before I proceed? For a stationary system, I have a question for you. If the system is a stationary, if the system, for example, is piston cylinder is a stationary. What do you think? What is the how you can summarize and simplify a change in energy of the system, delta of the system? How you simplify that? What can you say about that? If the system is a stationary, if your system, for example, is a piston cylinder and it is a stationary, how can we explain change of energy of the system? Anyone?
There will be any change of energy since there's no motion and there's no force being applied.
Exactly, because it's a stationary, there will be no change in potential energy or kinetic energy, right? It's a stationary, there's no velocity involved. So changing kinetic energy and changing potential energy is zero. And because we know change in energy of the system, that it has three parts: changing kinetic energy, changing potential, and changing internal. Kinetic energy is zero, changing kinetic energy, changing potential energy is zero. So it will be limited to changing internal energy, which is delta U, which is mu2 minus U1, right? So that's what you can. So you have to pay attention to, different cases and the assumptions, because later you're going to talk about, okay, if it's well insulated and it's adiabatic, if it's a stationary, so you should tailor the energy balance equation for different engineering devices based on the assumptions you have. I'm gonna stop at this point. So next time, which is next week, I'm gonna pick it up from here. Now I'm taking a question if there is any. Is there any question now?
Yeah, yes, I have a question.
Yes, please. And please talk a little bit louder. I can.
Okay. Can we have a syllabus for this class?
Yes, you will.
Okay.
Along with two sessions of the lecture and some selected problems from chapter 1. So all at once via email.
When should we expect to receive the email?
Tomorrow. The reason I haven't sent it yet, because to be honest, I changed my password and it just gave me a hard time. So I'm gonna send it tomorrow. Tomorrow is Thursday. Yes, Thursday I'm gonna send it out. Thursday by midnight.
Okay, thank you.
Sure. Any other question you may have? All right, then, if you don't have any question, I'm going to stop sharing and have a great weekend. And I'm going to send you the slideshow so you can review them over the weekend and we can, pick it up from where we left off next week. All right. If any of you guys wants to see me after the class, I'm right here.